Right now, scattered across the Milky Way, there are stellar corpses that are still glowing. Not because they're alive, not because anything is burning inside them. They're glowing because they haven't finished dying yet. These are white dwarfs, the dense leftover cores of dead stars. And they hold so much trapped heat that it will take them longer to cool down than the entire current age of the universe. We're talking about timescales so extreme that the universe as it exists today is essentially still in its infancy compared to what these objects need to fully fade. What happens to a white dwarf across trillions of years is one of the most haunting stories in all of astrophysics. And the strangest part is that nothing has ever witnessed the ending. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. There's a moment in the life of a star when everything changes. Not gradually, not gently. There's a point where the engine that has powered it for millions or billions of years simply runs out of fuel. And when that happens, the star doesn't just quietly go dark. It goes through a violent transformation. It sheds its outer layers. It throws off enormous shells of gas. And what's left behind is something extraordinary. A core. Just the core. Stripped bare. Incredibly hot. Incredibly dense. And utterly permanently dead. No fire burns inside it. No fusion reaction sustains it. It's a remnant, a leftover, an ember from a fire that has already gone out. That ember is what astronomers call a white dwarf, and the story of what happens to it across the longest timescales imaginable is one of the most quietly astonishing tales in all of physics. Because this object, this dead core, doesn't just sit there unchanged forever. It changes, slowly, relentlessly, over periods of time so vast that the entire current history of the universe barely registers as the opening chapter. To understand what a white dwarf is, you first need to understand what it came from. And that means understanding, at least briefly, how a star like our sun lives and dies. A star is, at its most basic, a battle. On one side, you have gravity, pulling every atom, every particle toward the center, trying to collapse the entire structure into as small a point as possible. On the other side, you have energy. Deep in the star's core, nuclear fusion is taking place. Hydrogen atoms are being smashed together under tremendous pressure and heat, fusing into helium and releasing enormous amounts of energy in the process. That energy radiates outward, pushing against gravity, holding the star up. This is what keeps a star stable for most of its life. Gravity pulls inward. Energy pushes outward. The two forces balance each other. And as long as fusion continues, the star holds its shape. Our sun has been doing this for about 4.5 billion years. It will continue doing it for roughly another 5 billion years. It's a remarkably stable process. Every second, the sun converts about 600 million tons of hydrogen into helium through nuclear fusion. That reaction produces an extraordinary amount of energy. More energy in a single second than all of human civilization has generated in its entire history. And this has been going on continuously for billions of years. But here's the crucial thing. The fuel is finite. There's a lot of hydrogen in the sun, but there isn't an infinite amount. Eventually, the hydrogen in the core runs low. When that happens, the balance between gravity and energy starts to shift. For a star like the sun, what follows is dramatic. As the hydrogen in the core becomes depleted, the core contracts under gravity. This contraction heats the core and the surrounding layers, and hydrogen in a shell around the core begins to fuse. The extra energy causes the outer layers of the star to expand enormously. The star swells into what's called a red giant. When our sun reaches this stage, roughly 5 billion years from now, it will expand so dramatically that it will likely engulf Mercury and Venus. Earth might survive on the edge of this expanded atmosphere, but it will be scorched and lifeless. The sun, as a red giant, will be a completely different object from the stable yellow star we know today. Its diameter will expand to perhaps 200 times its current size or more. If you could somehow stand far enough away to see the whole thing, you'd barely recognize it. But even this phase doesn't last forever. The star continues to burn through fuel. In its core, helium begins to fuse into heavier elements, primarily carbon and oxygen. This process generates energy, but it's less efficient than hydrogen fusion. The star is living on borrowed time. For a star with the mass of our sun, the process reaches a limit at carbon and oxygen. The core simply isn't massive enough and doesn't generate enough pressure and heat to fuse carbon and oxygen into anything heavier. The nuclear furnace has hit a wall, and now something remarkable happens. The star begins to lose its outer layers, not through an explosion, but through a process that's more like a slow exhalation. The outer layers of the red giant are only loosely bound by gravity. Stellar winds, pulsations, and thermal pressure push these layers outward into space. Over thousands of years, the star sheds its outer envelope, casting off enormous shells of gas that expand outward in all directions. These expanding gas shells, illuminated by the intense ultraviolet radiation from the exposed core, create what are called planetary nebulae. The name is misleading because they have nothing to do with planets. They're the discarded outer layers of dying stars, glowing beautifully in space, and at the center of each one sits the exposed core, the white dwarf. What you're left with after this process is an object that defies everyday intuition. A white dwarf is roughly the size of Earth, perhaps slightly smaller. Its diameter is typically around 7,000 to 8,000 miles. You could fit it comfortably within the volume of our planet. But here's what makes it extraordinary. Despite being Earth-sized, a white dwarf contains roughly the mass of the Sun. In some cases, even more. This means the density is almost incomprehensible. A single teaspoon of white dwarf material, if you could somehow scoop it up and bring it to Earth, would weigh somewhere in the neighborhood of 5 to 10 tons. Think about that for a moment. A teaspoon. The amount of sugar you might stir into a cup of tea, weighing as much as a large truck. And the entire object, every cubic inch of it, is this dense. The white dwarf is one of the densest forms of matter that exists in the known universe outside of neutron stars and black holes. If you placed a white dwarf on the surface of the Earth, assuming the Earth could somehow support it, it would immediately sink through the crust, through the mantle, through everything, because its weight is so far beyond anything the planet's surface could sustain. Now, the obvious question is this. If gravity is constantly trying to crush this object inward, and there's no fusion reaction pushing back, what holds it up? What prevents a white dwarf from collapsing into something even denser? The answer comes from quantum mechanics, specifically from something called electron degeneracy pressure. To understand this, you need to know about a principle in physics called the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state at the same time and place. When matter is compressed to the extreme densities found inside a white dwarf, the electrons are squeezed into the smallest possible space. but the Pauli exclusion principle says they can't all be in the same state. They resist being compressed further. This resistance creates a pressure, electron degeneracy pressure, that pushes back against gravity. It's not a thermal pressure like the radiation pressure that holds up a normal star. It doesn't depend on temperature. It's a quantum mechanical effect. Even if the white dwarf were cooled to absolute zero, this pressure would still exist. This is what makes a white dwarf fundamentally different from a normal star. A normal star is held up by energy generated through fusion. Turn off the fusion and the star collapses. A white dwarf is held up by the quantum mechanical behavior of its electrons. It doesn't need an energy source to maintain its structure. It will hold its shape essentially forever. This is a critical point because it means that a white dwarf is structurally stable. It won't collapse further under its own gravity, at least not unless additional mass pushes it over a critical threshold. That threshold is called the Chandrasekhar limit, named after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the early 1930s. The limit is approximately 1.4 times the mass of the Sun. Below this mass, electron degeneracy pressure can hold the white dwarf up indefinitely. Above it, the electrons can no longer resist gravity, and the object would collapse into something denser, either a neutron star or, through other processes, potentially trigger a catastrophic thermonuclear explosion. But most white dwarfs fall comfortably below this limit. The ones we observe in our galaxy have masses typically between about half the mass of the Sun and just over 1 solar mass. They're safely within the range where electron degeneracy pressure can support them, so they won't collapse. They'll hold their Earth-sized shape for an almost unimaginable span of time. But here's what makes the white dwarf story so fascinating. Even though the structure is stable, the white dwarf is not unchanging. It's incredibly hot. When a white dwarf is first exposed, when the outer layers of its parent star have just been shed, the surface temperature can be staggering. Some newly formed white dwarfs have surface temperatures exceeding 100,000 degrees Celsius. That's more than 17 times hotter than the surface of our Sun. They glow with an intense blue-white light, radiating furiously across the electromagnetic spectrum. The name white dwarf comes from this initial appearance. When astronomers first identified these objects, they appeared white because of their extreme heat. They're called dwarfs because they're physically small compared to other stars. Roughly Earth-sized rather than Sun-sized or larger. But in terms of temperature and luminosity, a freshly formed white dwarf is anything but dim. It blazes. And that heat is not being generated by any internal process. There's no fusion reaction producing new energy inside the white dwarf. The carbon and oxygen core is too cool and too low pressure to ignite further fusion. A tiny trickle of residual surface reactions might persist briefly after formation, but this is negligible and short-lived. What the white dwarf possesses is stored thermal energy, residual heat. The core of the star was subjected to enormous temperatures during its lifetime of fusion. Even after fusion stops, that heat doesn't vanish. It's trapped inside, locked in the dense lattice of carbon and oxygen ions, stored in the frantic motion of particles, held within the object by its own density and structure. A white dwarf is, in essence, a cosmic ember. A chunk of matter that was heated to extraordinary temperatures during the life of a star, and now, with no way to generate new heat, is slowly releasing what it has into the cold emptiness of space. And this is the key to everything that follows across the next trillions of years. The story of a white dwarf after it stops shining as an active star is entirely the story of cooling. Nothing else. No dramatic explosions, no sudden changes, no catastrophic events. Just heat, slowly, relentlessly, radiating away into the void. The white dwarf glows because it's hot. It radiates energy into space because the surface is hotter than the surrounding environment, which is the near vacuum of space at a temperature of just a few degrees above absolute zero. As it radiates, it loses energy. As it loses energy, it cools. As it cools, it glows less brightly. And this process continues year after year, century after century, millennium after millennium, eon after eon. The timescales involved are what make this story extraordinary. Because a white dwarf cools incredibly slowly. There are several reasons for this. First, the object is enormously dense. All that mass packed into such a small volume means there is a tremendous amount of thermal energy stored inside. The total thermal energy of a white dwarf is staggering, enough to keep it glowing for billions upon billions of years, even though it receives no new energy from any source. Second, the surface area through which it can radiate is relatively small. A white dwarf is only about the size of Earth. Compared to a normal star, which might be hundreds of thousands or even millions of miles across, the white dwarf has a tiny surface area. It's like trying to cool down a massive oven by opening a window the size of a postage stamp. The heat has to escape through a comparatively small surface, and that limits how quickly the object can cool. Third, as the white dwarf cools, the temperature difference between its surface and the surrounding space decreases, and the rate of radiation depends on this temperature difference. When the white dwarf is extremely hot, say 100,000 degrees, it radiates energy rapidly. But as it cools to 10,000 degrees, then 5,000, then 3,000, the rate of energy loss drops. Each successive drop in temperature takes longer than the one before. The cooling curve is not linear, it's logarithmic. The first 50% of the cooling happens relatively quickly. The last few percent takes an almost incomprehensible amount of time. Consider what this means in practical terms. The universe is currently about 13.8 billion years old. That's how long it has been since the Big Bang. Every star that has ever formed, every galaxy that has ever assembled, every planet that has ever coalesced from dust and gas, all of it has happened within this 13.8 billion year window. And in that time, the oldest white dwarfs in the universe, the ones that formed from the very first generations of stars that lived fast and died young, have barely begun to cool. They're still glowing, still radiating, still thousands of degrees at their surfaces. They have been cooling for perhaps 10 or 11 billion years, and they're nowhere near finished. Not even close. They're not even a meaningful fraction of the way through their cooling journey. The cooling process for a typical white dwarf is estimated to take somewhere on the order of a quadrillion years or more to reach its theoretical endpoint. A quadrillion is a 1 followed by 15 zeros. That's roughly 100,000 times the current age of the universe. To put this in perspective, imagine that the entire history of the universe up to this moment, all 13.8 billion years of it, is represented by a single step in a journey. The total cooling time of a white dwarf would be a journey of roughly 100,000 steps. We've taken one step. One single step out of 100,000. The white dwarf has barely started. This is what makes the white dwarf one of the most patient objects in all of nature. It doesn't do anything dramatic, It doesn't explode, it doesn't collapse, it doesn't transform into something else through any sudden process. It just sits there, in the dark vacuum of space, quietly releasing heat, photon by photon, degree by degree, over timescales that dwarf every other process in the cosmos. And it will keep doing this long after every star in the Milky Way has burned out. Long after the last red dwarf, those tiny dim stars that burn their fuel so slowly they can last for trillions of years, has finally exhausted its hydrogen and died. Long after the galaxies themselves have gone dark, the white dwarfs will still be there, still faintly glowing, still cooling. There are roughly 10 billion white dwarfs in the Milky Way right now. About 97% of all stars in the galaxy will eventually end their lives as white dwarfs. Only the most massive stars, those born with more than about 8 times the mass of the Sun, will end as neutron stars or black holes. Everything else becomes a white dwarf. That means our Sun will become a white dwarf. About 5 billion years from now, after it swells into a red giant and sheds its outer layers, the core of the Sun will be exposed as a white dwarf, roughly the size of Earth, with about half the Sun's current mass. And that white dwarf will begin its own long, quiet journey of cooling. A journey that will last far longer than the Sun ever shone as a living star. Think about that. Our Sun has been burning for about 4.5 billion years. It will burn for about another 5 billion. Total lifetime as an active, fusion-powered star, roughly 10 billion years. But as a white dwarf, the remnant of the Sun will persist for quadrillions of years. The active life of the star is a brief, brilliant flash compared to the immense dark aftermath of the white dwarf stage. It's like a firework. A few seconds of dazzling light followed by hours of slowly fading warmth from the spent casing. Except, in this case, the flash lasts 10 billion years, and the fading warmth lasts 100,000 times longer. And this is true for every sun-like star in the universe. Every yellow dwarf, every orange dwarf, every star that doesn't have enough mass to explode as a supernova. They will all become white dwarfs. They will all begin the same cooling journey. They will all slowly fade across timescales that make the current age of the universe look like the blink of an eye. Sirius B, the white dwarf companion of Sirius, the brightest star in our night sky, is one of the closest and best studied white dwarfs. It has a surface temperature of about 25,000 degrees Celsius and a mass of roughly 1 solar mass compressed into a volume about the size of Earth. It formed roughly 120 million years ago, when its parent star, which was once much more massive and luminous than our Sun, reached the end of its life. In 120 million years of cooling, Sirius B has dropped from perhaps its initial temperature of over 100,000 degrees to 25,000 degrees. It's still intensely hot, still glowing a brilliant blue-white, still radiating significant energy into space, and it has trillions upon trillions of years of cooling ahead of it. I Capeg b is another well-known white dwarf. It has a mass that puts it within striking distance of the Chandra-Shekhar limit, at roughly 1.15 solar masses. Its surface temperature is around 35,000 degrees Celsius. This white dwarf is interesting because if it accretes enough mass from its companion star to push it over the limit, it could potentially trigger a Type 1a supernova, one of the most powerful explosions in the universe. But barring that dramatic fate, it too will follow the same path. Slow, relentless cooling over timescales that defy human comprehension. There is something profound about contemplating an object whose primary activity is simply losing heat. We're used to thinking about the universe in terms of action: stars igniting, galaxies colliding, supernovae exploding, black holes consuming matter. These are dramatic, violent, energetic events. They capture our imagination because they're powerful and transformative. But a white dwarf cooling is the opposite of all that. It's quiet. It's patient. It's almost meditative. Nothing happens quickly. Nothing happens dramatically. The change is so gradual that if you could somehow watch a white dwarf for 1,000,000 years, you barely notice any difference. Its color might shift imperceptibly. Its brightness might dim by a tiny fraction. But to your eyes, it would look the same. The changes are real, but they're spread across such vast timescales that they become invisible on any human scale. And yet, these changes are inevitable. The white dwarf cannot stop cooling. It has no mechanism to generate new heat. The laws of thermodynamics are absolute. Heat flows from hot object to cold surroundings. The white dwarf is hot. Space is cold. Heat will flow. There is no escape from this. No reprieve, no second act. The white dwarf will cool and cool and cool until eventually, in the incomprehensibly distant future, it reaches thermal equilibrium with the universe around it. That process, from blazing ember to cold, dark remnant, is what we're going to follow across the rest of this story. Because what happens along the way, the physical changes the white dwarf undergoes as it cools, the transformations in its structure and appearance, the way it interacts with the dying universe around it, all of it is extraordinary. Not because it's dramatic, but because of what it reveals about the nature of time, the fate of matter, and the ultimate destiny of every sun-like star that has ever existed or ever will exist. The white dwarf sitting quietly in the darkness, slowly releasing its stored heat into the void, is one of the most important objects in the future history of the cosmos, and its story is only just beginning. So the white dwarf sits in space. No fusion, no engine, no source of new energy, just an Earth-sized ball of carbon and oxygen so dense that a teaspoon of it would weigh several tons, glowing fiercely with heat that was stored during the billions of years its parent star was alive. And now that heat has nowhere to go but out. Out through the surface, out into the vacuum, photon by photon, degree by degree, across spans of time so long that the human mind has no real framework for holding them. This process, this cooling, sounds simple. And in principle, it is simple. A hot object in a cold environment radiates energy and gets cooler. You experience this every day. A cup of coffee left on a counter cools down. A stove burner turned off fades from red to black. These are everyday examples of the same basic physics. But the cooling of a white dwarf is different from the cooling of anything you've ever encountered. Not because the physics is different, but because of the scales involved. The temperatures are extreme, the densities are beyond anything on Earth. The timescales stretch across billions and eventually trillions of years. And the way the cooling unfolds, speeding up and slowing down in response to changes happening deep inside the star, reveals physics that took astronomers decades to fully understand. Let's start with what happens in the first phase of cooling, the relatively early period after the white dwarf is first exposed. When a white dwarf is born, freshly revealed by the shedding of its parent star's outer layers, it is extraordinarily hot. Surface temperatures can exceed 100,000 degrees Celsius. At these temperatures, the white dwarf radiates powerfully, mostly in ultraviolet light and even soft X-rays. It's pouring energy into space at an enormous rate. If you could see it up close, it would be blindingly bright, a tiny point of searing blue-white light. During this initial phase, the cooling is relatively fast by astronomical standards. The key word there is relatively. We're still talking about millions of years for noticeable changes, but compared to what comes later, this early cooling is almost brisk. Within the first 100 million years or so, a white dwarf might cool from 100,000 degrees to perhaps 40 or 50,000 degrees at its surface. That's a dramatic drop in absolute terms, but the object is still incredibly hot, still glowing intensely, still radiating strongly in the ultraviolet. Within the first billion years, the surface temperature might drop further, perhaps to around 20,000 degrees. This is still hotter than the surface of most stars. The white dwarf at this point would still appear as a brilliant blue-white point of light, still easily visible, still radiating significant energy. After several billion years, the surface temperature might be in the range of 10,000 to 15,000 degrees Celsius. This is roughly the temperature of the surface of a hot main sequence star. The white dwarf is dimmer now, noticeably so compared to its youth, but still glowing white. Still putting out light in the visible spectrum. Still very much present in the sky of any planet close enough to see it. Now, here's where the physics becomes fascinating. You might expect that if a white dwarf drops from 100,000 degrees to 20,000 degrees in its first billion years, then it should drop from 20,000 to 0 in another few billion years. But that's not what happens. Not even close. The cooling slows down dramatically as the temperature drops. Each successive degree of cooling takes longer than the one before. And the reason for this is built into the fundamental physics of how radiation works. The rate at which a hot object radiates energy into space is governed by a relationship that physicists call the Stefan-Boltzmann law. This law tells us that the amount of energy radiated by an object is proportional to the surface area of the object multiplied by the fourth power of its surface temperature. The fourth power, that's the critical part. It means that if you double the temperature, the radiation rate doesn't just double, it increases by a factor of 16. 2 to the fourth power is 16. Conversely, if you cut the temperature in half, the radiation rate drops by a factor of 16. This has enormous consequences for a cooling white dwarf. When the white dwarf is very hot, at 100,000 degrees, it radiates energy at a phenomenal rate. The fourth power of 100,000 is a colossal number. Energy pours off the surface. Cooling is rapid, but as the white dwarf cools, the radiation rate drops sharply. At 50,000 degrees, the radiation rate is only 1/16 of what it was at 100,000 degrees. At 25,000 degrees, it's 1/16 of that, which is 1/256 of the original rate. At 10,000 degrees, the radiation rate is a tiny fraction of what it was when the white dwarf was young. The cooler the white dwarf gets, the less energy it radiates per second. And the less energy it radiates per second, the longer it takes to cool further. The cooling process is self-throttling. It slows itself down as it proceeds. This is why the early cooling happens relatively quickly, and the later cooling takes almost forever. The white dwarf approaches its final temperature asymptotically, getting closer and closer, but never quite reaching it on any time scale that matters. Think of it like a car approaching a wall. At first, the car moves quickly. Then it decelerates. Then it moves more and more slowly, closer and closer to the wall, but never quite touching it. The white dwarf approaches absolute coldness the same way, closer and closer, slower and slower, across spans of time that grow longer and longer. But the Stefan Boltzmann law is only part of the story. The law describes how energy leaves the surface, but what's happening inside the white dwarf as it cools is equally important, and in some ways even more remarkable. Because the interior of a white dwarf is not just a uniform ball of hot material that gradually cools from the outside in. It's a complex physical system with distinct layers, different thermal properties, and internal processes that dramatically affect the cooling rate. The deep interior of a white dwarf, the core, is primarily composed of carbon and oxygen nuclei arranged in a state that physicists call a Coulomb plasma. At the temperatures present in a young white dwarf, these ions are not locked in place. They're vibrating intensely, jostling against each other, carrying thermal energy in their motion. The electrons, which provide the degeneracy pressure that holds the star up, are actually excellent conductors of heat. In fact, the electrons in a white dwarf conduct heat so efficiently that the interior is nearly isothermal, meaning the temperature is almost the same everywhere inside the core. Heat moves through the interior very quickly, carried by the degenerate electron gas. This means that the bottleneck for cooling is not in the interior. The interior can transport heat very efficiently. The bottleneck is at the surface. Surrounding the carbon-oxygen core is a thin outer layer composed mostly of helium, and above that an even thinner layer of hydrogen. These non-degenerate outer layers act as an insulating blanket. They're not as efficient at conducting heat as the degenerate core. They slow down the rate at which internal heat can escape to the surface and be radiated away. So the white dwarf is like a superheated ball wrapped in a thin blanket. The ball wants to radiate its heat, but the blanket slows the process. The thicker and more opaque the blanket, the slower the cooling. As the white dwarf ages and cools, the properties of this insulating envelope change. The opacity, the degree to which the outer layers block the flow of energy, varies with temperature and composition. This means the cooling rate is not just governed by the Stefan Boltzmann law at the surface, but also by the complex physics of energy transport through the outer envelope. Astronomers have spent decades building detailed computer models of white dwarf cooling that account for all these factors. The models track the temperature throughout the entire structure of the white dwarf, from the core to the surface, calculating how heat flows outward through the insulating layers and how quickly it's radiated away at the surface. These models have become remarkably sophisticated, and they agree well with observations of real white dwarfs. And those observations have revealed something extraordinary. As a white dwarf cools through certain temperature thresholds, something dramatic happens deep inside its core. Something that changes the physical structure of the star itself. It crystallizes. Yes, crystallizes. The core of the white dwarf, this ball of carbon and oxygen ions that has been in a plasma state, a state where the ions are free to move and vibrate, begins to solidify. The ions start locking into a regular, repeating lattice structure, a crystal, like ice forming in water, like a diamond forming from carbon under pressure, except this crystal is Earth-sized, and it's forming inside a dead star. The physics behind this crystallization is actually well understood. At very high temperatures, the carbon and oxygen ions in the core have so much kinetic energy that they move freely, bouncing off each other in a disordered plasma. But as the core cools, the ions lose kinetic energy. They slow down, and at some point, the electrostatic repulsion between the positively charged ions becomes more important than their thermal motion. The ions begin to settle into fixed positions relative to each other, arranging themselves into the lowest energy configuration, which is a regular crystal lattice. Physicists predicted this would happen decades before it was observationally confirmed. The theory was worked out by several researchers over the course of the 20th century, building on fundamental principles of condensed matter physics and plasma physics. They calculated that for a typical carbon-oxygen white dwarf, crystallization should begin when the core temperature drops to roughly 6 million degrees Celsius. That's still incredibly hot by any earthly standard, but it's cool enough that the ions no longer have sufficient thermal energy to remain in a disordered state. Crystallization doesn't happen all at once. It begins at the center of the white dwarf, where the pressure and density are highest, and gradually works its way outward as the core continues to cool. Over time, more and more of the interior solidifies, building an ever-growing crystal sphere at the heart of the dead star. This process takes hundreds of millions to billions of years, depending on the mass and composition of the white dwarf. And here's the part that has significant consequences for the cooling timeline. When a material crystallizes, it releases latent heat. This is the same principle you see when water freezes. Liquid water at 0 degrees Celsius must release a certain amount of energy before it can solidify into ice. That released energy is latent heat. In the case of a white dwarf, the amount of latent heat released during crystallization is enormous. It's equivalent to a significant fraction of the total thermal energy remaining in the core at the time crystallization begins. This released latent heat acts as an additional energy source. It doesn't generate new energy from fusion or any other nuclear process. It's simply stored energy being released as the phase transition occurs. But its effect on the cooling timeline is profound. The latent heat temporarily slows down the cooling of the white dwarf, adding roughly 1 to 2 billion years to the total cooling time. The white dwarf essentially pauses on its cooling journey, lingering at a particular temperature range while the latent heat from crystallization is gradually radiated away. It's like a hiker walking downhill who suddenly encounters a flat plateau. The descent doesn't stop. It just slows down for a while before resuming. There's another effect that accompanies crystallization and further influences the cooling process. When the core crystallizes, the composition of the solid crystal can differ from the composition of the surrounding liquid. In a carbon-oxygen white dwarf, the crystal lattice preferentially incorporates oxygen, since oxygen is heavier and tends to settle into the lattice more readily under these conditions. This means that as crystallization proceeds, the liquid surrounding the growing crystal becomes enriched in carbon. Carbon is lighter than oxygen, so this carbon-enriched liquid is buoyant. It rises toward the outer regions of the core, while the heavier, oxygen-enriched crystal sinks toward the center. This process is called gravitational settling, or sometimes chemical fractionation. The net result is that the core of the white dwarf becomes compositionally stratified. The center becomes oxygen-rich, and the outer core becomes carbon-rich. This redistribution of elements releases additional gravitational potential energy, which is converted to heat. So not only does the crystallization itself release latent heat, but the accompanying settling of elements releases even more energy. Both of these effects conspire to slow the cooling of the white dwarf significantly. In 2019, astronomers announced that they had found direct observational evidence for crystallization in white dwarfs. Using data from the Gaia Space Observatory, a European Space Agency mission that has been mapping the positions, distances, and properties of over 1 billion stars in the Milky Way with unprecedented precision, researchers identified a distinctive pattern in the population of white dwarfs. When they plotted the luminosities and colors of thousands of white dwarfs on a diagram, they found an excess of white dwarfs at a specific luminosity range. The way this works is surprisingly intuitive. If white dwarfs cooled smoothly and continuously, you would expect to find them spread evenly across all luminosity levels, because each one would pass through any given brightness at roughly the same speed on its way to dimmer and dimmer states. But if something slows the cooling at a particular temperature, if the white dwarfs linger at a certain brightness for longer than expected, then you'd find more white dwarfs piled up at that brightness. It's like cars on a highway. If traffic flows smoothly, cars are spread evenly along the road. But if there's a speed bump, cars bunch up around it because they all slow down at the same point. The Gaia data showed exactly this kind of bunching. There was a clear, statistically significant excess of white dwarfs at the luminosity range where crystallization models predicted they should linger. The pileup was not subtle. It stood out clearly in the data, a conspicuous clustering that smooth cooling models could not explain. Only when crystallization and its associated release of latent heat were included in the models did the predicted distribution match what Gaia actually observed. More white dwarfs were piling up at certain temperatures than the models predicted if cooling was smooth and continuous. This pileup matched exactly the predictions of crystallization theory. The white dwarfs were lingering at the luminosities where crystallization was expected to occur, spending extra time at those temperatures because of the latent heat being released. It was a beautiful confirmation of a prediction that had been made decades earlier. The dead cores of stars really were crystallizing, forming enormous crystals of carbon and oxygen deep in their interiors. And this process was measurably affecting how quickly they cooled. One particular white dwarf has become famous in this context. BPM 37093, sometimes given the nickname Lucy after the Beatles' song Lucy in the Sky with Diamonds, is a massive white dwarf located about 50 light-years from Earth in the constellation Centaurus. It has a mass of roughly 1.1 times the mass of the Sun, and a surface temperature of about 12,000 degrees Celsius. Based on its mass and temperature, astronomers believe that a substantial fraction of its interior has already crystallized. Because of its carbon-rich composition, the crystallized core is essentially a giant diamond. Not a diamond in the jewelry sense, of course. You couldn't cut it or wear it. It's buried deep inside a star, compressed to unimaginable densities at temperatures that would vaporize any earthly material. But structurally, the carbon atoms are arranged in a crystal lattice, similar to a diamond. The idea that dead stars contain cores that are essentially enormous diamonds captured the public imagination when it was first proposed, and has remained one of the most evocative images in modern astrophysics. Beyond crystallization, there are other processes that influence a white dwarf's cooling as it ages into the billions of years. The composition of the outer envelope matters enormously. White dwarfs with thicker hydrogen layers tend to cool more slowly, because hydrogen is a better insulator at certain temperatures. White dwarfs that have lost most of their hydrogen, perhaps stripped it away during interactions with a companion star or through other processes, cool faster because their insulating blanket is thinner. The mass of the white dwarf also affects its cooling rate. More massive white dwarfs have higher internal densities and crystallize earlier, which means they go through their crystallization-induced slowdown sooner. Less massive white dwarfs take longer to reach the crystallization threshold, and so cool more smoothly for a longer initial period before hitting that plateau. There is also the question of residual nuclear burning. Some white dwarfs, particularly young ones, still have a thin shell of hydrogen on their surfaces that can undergo a trickle of nuclear fusion. This fusion is not the sustained, powerful process that occurs in a main sequence star. It's a faint, sputtering reaction, barely detectable, but it does produce a small amount of energy, and that energy can slow the cooling slightly during the early phases of the white dwarf's life. Over time, this residual fuel is consumed, and the tiny trickle of fusion stops entirely. But for the first few 100 million years, it can make a measurable difference. All of these effects combined mean that the cooling of a white dwarf is not a simple, smooth decline from hot to cold. It's a complex process with different phases, each governed by different physics. The early cooling is dominated by the enormous initial temperature and the high radiation rate. Then, as the surface temperature drops and the radiation rate plummets due to the fourth power law, the cooling slows. Then crystallization begins, releasing latent heat and gravitational energy, slowing the cooling even further. Then, as crystallization completes and the latent heat is exhausted, the cooling resumes, but now at the agonizingly slow rates dictated by the ever-decreasing temperature difference between the white dwarf and the surrounding void. Astronomers have turned this complexity into a tool. Because the cooling rate of a white dwarf is predictable, at least in principle, the temperature of a white dwarf can tell you how old it is. A hot white dwarf is young. A cool white dwarf is old. By measuring the surface temperature and luminosity of a white dwarf and comparing it to theoretical cooling models, astronomers can estimate how long ago it formed. This technique is called white dwarf cosmochronology, and it's one of the most powerful methods for determining the ages of stellar populations. If you find a cluster of stars and identify the coolest, faintest white dwarfs in that cluster, you can estimate how long ago the first stars in that cluster died and became white dwarfs. This gives you a minimum age for the cluster. The technique has been applied to globular clusters, those ancient dense collections of hundreds of thousands of stars that orbit the Milky Way. Globular cluster NGC6397, for example, contains some of the faintest and coolest white dwarfs ever observed. By analyzing these dim remnants, astronomers have estimated that the cluster is roughly 12 to 13 billion years old, consistent with other methods of age determination. This is remarkable. We're using the slowly fading embers of dead stars as cosmic clocks, reading their temperatures like the hands of a clock that moves with glacial slowness across the eons. But there's a limit to what we can currently observe. The coolest white dwarfs we've detected have surface temperatures of around 3,000 to 4,000 degrees Celsius. That's still quite hot. It's roughly the temperature of a red dwarf star's surface, or the temperature of a glowing electric stove element. These cool white dwarfs appear as very faint, very red points of light. They're at the edge of what our telescopes can detect. Below about 3,000 degrees, a white dwarf would be radiating mostly in the infrared, becoming extremely difficult to see with optical telescopes. We might detect them with infrared observatories, but they'd be among the faintest objects in the sky. And here's the profound realization that emerges from all of this. Even these coolest observed white dwarfs, the ones hovering around 3,000 to 4,000 degrees, are not particularly old. Based on cooling models, they're roughly 10 to 12 billion years old. That's close to the age of the universe itself. The universe has only existed for 13.8 billion years. In all that time, the oldest white dwarfs have only managed to cool to a few thousand degrees. They're still glowing, still radiating, still visibly hot, at least with sensitive instruments. This tells us something staggering about the timescale of white dwarf cooling. 13.8 billion years, the entire age of the cosmos, is not enough time for any white dwarf anywhere in the observable universe to cool to the point where it stops emitting detectable light. Not a single one. Every white dwarf that has ever formed is still warm, still radiating, still somewhere on the early part of its cooling curve. The universe is simply too young for the cooling process to have reached its conclusion. The final state, the completely cooled remnant, remains theoretical. It has never been observed because it has never had time to come into existence. We know it will happen. The physics demands it. A white dwarf with no energy source must eventually radiate all its heat into space and reach thermal equilibrium with its surroundings. But the timescale required is so immense, so far beyond the current age of the universe, that this endpoint exists only in our equations, not in reality. Not yet. This gap between what physics predicts and what the universe has had time to produce is one of the most extraordinary things about white dwarfs. We can calculate exactly what will happen to these objects. We can model their cooling curves with precision. We can predict their temperatures at any point in the future, millions of years from now, billions of years from now, trillions of years from now. But we cannot observe the outcome because the universe hasn't existed long enough. We're watching a process that has barely started, a story whose first chapter is still being written, and the later chapters, the ones where the white dwarf truly begins to change in profound ways, where its light fades below visibility, where its surface cools to the temperature of a warm bath and then to the temperature of a cold room, and then to the temperature of deep space itself, those chapters won't be written for eons that make the current age of the cosmos look fleeting. And yet the white dwarf doesn't know any of this. It doesn't know that it's patient. It doesn't know that it's remarkable. It simply exists, following the laws of physics, radiating its stored heat into the void, one photon at a time. Each photon carries away a tiny amount of energy. Each photon makes the white dwarf imperceptibly cooler, and the next photon will carry slightly less energy than the last, because the surface is now slightly cooler, and a cooler surface emits slightly less energetic photons. The process feeds back on itself, slowing down with every passing moment. It is the most uneventful process in the cosmos. Nothing to witness, nothing to react to. A transfer of energy so gradual that it makes geological change look frantic, playing out across timescales that reduce everything else in cosmic history to a footnote. The formation of galaxies, the ignition and death of stars, the rise of life on planets, all of these events happen in the blink of an eye compared to the time a white dwarf takes to cool. The white dwarf outlasts them all, not through strength, not through power, but simply through patience, through the sheer, staggering slowness of its decline. It is the ultimate expression of thermodynamics in action. a system approaching equilibrium at a pace that makes eternity itself feel like a reasonable unit of measurement. And what does this cooling look like from the outside? What would you see if you could somehow watch a white dwarf over these inconceivable stretches of time? That's what comes next. Because the visible changes, the transformation from a brilliant blue-white point of light to something darker, dimmer, and eventually invisible, tell the story of cooling in a way that numbers alone cannot. The white dwarf doesn't just cool, it fades. And the way it fades, the colors it passes through, the thresholds it crosses as its light diminishes, reveals the full, haunting scope of what it means for a star to truly die. If you could somehow compress trillions of years into a time lapse, watching a white dwarf from the moment of its birth to the farthest reaches of its future, the most striking thing you'd notice wouldn't be a sudden event. It wouldn't be a flash or an explosion or a collapse. It would be a color change. A slow, achingly gradual shift in the light the object emits. A transition so smooth, so continuous, that at no single moment could you point to it and say something just happened. And yet, across the full span of the time lapse, the transformation would be total. From a searing blue-white point of brilliance to something you can no longer see at all. The white dwarf doesn't vanish. It fades. And the way it fades tells you everything about what's happening inside it. When a white dwarf is young, freshly exposed after its parent star has shed its outer layers, it glows blue-white. The surface temperature is so extreme, sometimes exceeding 100,000 degrees Celsius, that the peak of its radiation falls in the far ultraviolet. Most of the energy it's releasing isn't even visible to human eyes. It's too energetic, too far into the ultraviolet part of the electromagnetic spectrum. If you could see in ultraviolet, a newborn white dwarf would be blinding. In visible light, it appears as an intensely bright, blue-white point, the hottest shade a stellar object can display. Blue, in the language of stellar colors, means hot. It means the atoms on the surface are radiating photons with very short wavelengths, very high energies. The hotter the surface, the shorter the peak wavelength, and the bluer the light appears. As the white dwarf cools through its first billion years or so, the surface temperature drops from that initial extreme down to something in the range of 15 to 20,000 degrees Celsius. At these temperatures, the white dwarf still appears white to the human eye, perhaps with a faint blue tint. It's still very hot, still radiating strongly, still a conspicuous presence in the sky of any nearby planetary system. The color change from blue-white to pure white is subtle. You probably wouldn't notice it without precise instruments, but it's there. The peak wavelength of the radiation has shifted slightly toward longer wavelengths, slightly toward the red end of the spectrum. The photons leaving the surface carry a little less energy on average than they did a billion years earlier. After several billion more years of cooling, the surface temperature drops further, down to around 10,000 degrees, then 8,000, then 6,000. At 6,000 degrees Celsius, the white dwarf has roughly the same surface temperature as our sun. It would appear yellowish white, like sunlight. This is a meaningful milestone, not because anything special happens physically, but because the white dwarf has cooled to the temperature of an ordinary living star. Except, of course, it isn't a living star. It's far smaller, far denser, and it has no fusion engine keeping it warm. It has simply taken this long, billions of years, for its stored heat to drain away, to the point where its surface matches the temperature of a mid-sized main sequence star. And the universe is still young enough at this point. We're only perhaps 8 to 10 billion years into the white dwarf's cooling journey. The cosmos around it is still full of active stars, still bright, still bustling with stellar activity. Galaxies are still forming stars. Nebulae are still collapsing into new solar systems. The white dwarf, cooling quietly in the background, is easy to overlook amid all this activity. But the cooling doesn't stop at 6,000 degrees. It continues, always continues. And as the surface temperature drops below 6,000 degrees, the color shifts more noticeably. 5,000 degrees gives the white dwarf a distinctly yellow appearance. 4,500 degrees pushes it into orange. 4,000 degrees into a deep, warm orange that borders on red. At 3,500 degrees, the white dwarf glows a dull red, like a cooling ember in a fireplace. This is roughly the surface temperature of the coolest red dwarf stars. Those tiny dim stars that make up about 70% of all stars in the Milky Way. But a red dwarf achieves this temperature while actively fusing hydrogen in its core. The white dwarf reaches it through pure cooling, through the slow surrender of stored energy accumulated over the lifetime of its long-dead parent star. Below 3,000 degrees, the white dwarf enters a regime that astronomers have only recently begun to probe. At these temperatures, the peak of the object's radiation has shifted decisively out of the visible spectrum and into the infrared. The white dwarf is no longer white at all. It's barely even red. To the naked human eye, standing at a reasonable distance, the object would appear extremely dim. A faint reddish smudge perhaps, or possibly invisible altogether. Your eyes simply aren't sensitive enough to detect the low energy photons it's emitting. This transition from visible light to infrared radiation is one of the most significant thresholds in the white dwarf's cooling journey. It marks the point where the object effectively disappears from ordinary view. It hasn't gone anywhere. It hasn't collapsed or exploded or been consumed by anything. It's still there. The same mass, the same density, the same Earth-sized sphere of crystallized carbon and oxygen. But it has become invisible. Not because it has stopped radiating, but because the radiation it produces is no longer the kind that eyes or optical telescopes can detect. This is what it means for a star to truly die in the most practical sense. Not the dramatic death of a supernova, not the catastrophic collapse into a black hole, but the quiet, almost imperceptible fading from visibility. The light just gets dimmer and dimmer, redder and redder, until it slips below the threshold of detection, and the object vanishes from the visible universe. The physics behind this color shift is described by a principle known as Wien's displacement law. This law states that the wavelength at which a hot object emits the most radiation is inversely proportional to its temperature. The hotter the object, the shorter the peak wavelength. The cooler the object, the longer the peak wavelength. When a white dwarf is at 100,000 degrees, its peak emission is in the far ultraviolet, at wavelengths around 30 nanometers. At 10,000 degrees, the peak has shifted to about 300 nanometers, still in the ultraviolet but close to visible blue light. At 6,000 degrees, the peak is around 500 nanometers, solidly in the visible range, producing yellow-white light. At 3,000 degrees, the peak is around 1,000 nanometers, which is in the near-infrared, just beyond what human eyes can see. And at 1,000 degrees, The peak shifts to about 3,000 nanometers, deep into the infrared. The object is still radiating, still emitting photons, but those photons are low-energy, long-wavelength infrared photons that pass right through the world of visible light, as if they don't exist. From a human perspective, they might as well not exist. The white dwarf has become a source of gentle warmth, not light. If planets survived the death of the parent star, if any rocky worlds endured the red giant phase by orbiting far enough away, or migrated inward afterward, they would still be circling the white dwarf during this long fade. And they would be freezing. Slowly, imperceptibly, but inevitably. In the early stages, when the white dwarf was still hot, a close orbiting planet might have received enough warmth to maintain liquid water on its surface. Some astronomers have even speculated that the habitable zone of a young white dwarf, though narrow, could persist for several billion years. But as the white dwarf cools through the thousands of degrees and into the hundreds, that habitable window closes. Any oceans freeze solid. Any atmosphere thin enough to depend on the white dwarf's warmth would condense and collapse onto the surface. The planet wouldn't be destroyed. It would simply go cold, following its star into the dark. Two objects, star and world, cooling together in silence. Now, let's push further into the future. Let's move beyond the timescales that the current universe has had time to explore, and into the deep future, tens of billions of years from now, then hundreds of billions, then trillions. As the white dwarf continues to cool below 1,000 degrees Celsius, it fades deeper and deeper into the infrared. Its luminosity, the total amount of energy it radiates per second, drops to astonishingly low levels. A freshly formed white dwarf might have a luminosity that is a significant fraction of the sun's, maybe 1% or even 10% of solar luminosity in some cases. By the time it's cooled to a few thousand degrees, its luminosity is down to perhaps 1/1,000,000th or 1/10,000,000th of the sun's. At a few hundred degrees, the luminosity drops to levels so low that the numbers become almost comical in their smallness. 1/1,000,000th of solar luminosity. 1/4,000,000th. Numbers so tiny that they become difficult to express in any meaningful way. But the object is still radiating. Thermodynamics demands it. Any object above absolute zero radiates electromagnetic energy. A human body at 37 degrees Celsius radiates in the infrared. A warm rock radiates. Even a cold rock radiates, just very faintly. The white dwarf, as it cools through hundreds of degrees, then tens of degrees, approaches a state where it radiates with the feebleness of a warm stone. Except this warm stone has the mass of a star. It contains roughly half the mass of the sun packed into a volume the size of Earth, and it's putting out less energy than a household light bulb. Meanwhile, the universe around the white dwarf is changing too. And this context matters enormously for understanding what the white dwarf's fading really means. Because the white dwarf isn't fading in isolation. It's fading in a universe that is itself growing darker. The current age of the universe, 13.8 billion years, places us in what astronomers sometimes call the stelliferous era, the age of stars. This is the period in cosmic history when stars are actively forming, burning, and dying. Galaxies are full of light. Star-forming nebulae are producing new solar systems. The universe is by any measure bright and active, but this era will not last forever. Star formation depends on the availability of cold gas, the raw material from which stars condense. And the supply of cold gas in galaxies is finite. Every time a new star forms, it uses up some of that gas. Some of the gas is returned to the interstellar medium when stars die, through stellar winds and supernova explosions. But not all of it. Some is locked up permanently in white dwarfs, neutron stars, and black holes. Some is ejected from galaxies entirely. Over time, the supply dwindles. Estimates suggest that the rate of star formation in the universe has already peaked. It peaked roughly 10 to 11 billion years ago, when the universe was only about 3 billion years old. Since then, the rate has been declining. Today, the Milky Way forms roughly 1 or 2 new stars per year. That might sound like a lot, but compared to the billions of stars already in the galaxy, it's a trickle. And the rate will continue to decline. In tens of billions of years, star formation in the Milky Way and most other galaxies will have slowed to a crawl. In 100 billion years, it will have essentially stopped. The last generation of stars will have formed, and once those stars exhaust their fuel, no new ones will replace them. The longest-lived stars in the universe are the red dwarfs, those small dim stars that burn their hydrogen so slowly they can last for trillions of years. A red dwarf with about 10% of the Sun's mass has a predicted lifetime of roughly 10 trillion years. That's nearly 1,000 times the current age of the universe. These tiny, patient stars will be the last lights burning in the cosmos. Long after every sun-like star has become a white dwarf, long after every massive star has exploded as a supernova and collapsed into a neutron star or black hole, the red dwarfs will still be shining. Faintly, dimly, but persistently. They will be the final embers of the stelliferous era. But eventually, even the red dwarfs will run out of fuel. The last red dwarf in the universe will exhaust its hydrogen, grow hotter and bluer as it contracts, and eventually fade into a small helium-white dwarf remnant that then begins its own long cooling journey. And when that happens, the stelliferous era will be over. No more stars, no more fusion, no more light generated by nuclear reactions anywhere in the observable universe. The cosmos will enter a new era, sometimes called the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, black holes, cold, dark objects drifting through an expanding, cooling universe. This is the context in which the white dwarf's long fading takes on its full significance. Because by the time the white dwarf has cooled to a few hundred degrees, to the point where it's radiating only in the deep infrared, the universe around it will have changed beyond recognition. The bright, bustling cosmos we see today will be gone. The galaxies will still exist as gravitationally bound structures, but they will be dark. Their stars will have burned out. The gas between stars will have been consumed or expelled. The only objects remaining will be the remnants, drifting through a void that grows emptier and colder with each passing eon as the universe continues to expand. In this dark future universe, the white dwarf is still there, still cooling, still radiating its feeble infrared glow, but now there's nothing else to compare it to. No living stars shining nearby, no nebulae glowing with the light of newborn solar systems. The white dwarf, dim as it is, might actually be one of the warmer objects in its vicinity. The cosmic microwave background radiation, the leftover glow from the Big Bang that currently fills the universe at a temperature of about 2.7 Kelvin, will have cooled even further as the universe expands. Trillions of years from now, the background temperature of the universe will be a tiny fraction of a degree above absolute zero, and the white dwarf, even one that has cooled to just a few tens of degrees above absolute zero, will still be warmer than its surroundings. It will still be radiating, still losing heat, but the temperature difference between the white dwarf and the universe will be so small that the rate of cooling will be almost imperceptible. This is where the asymptotic nature of the cooling process becomes almost philosophically significant. The white dwarf approaches the temperature of its surroundings, but never quite reaches it on any finite timescale. It's like a mathematical curve that approaches a line but never touches it. Each degree of cooling takes longer than the last. Each fraction of a degree takes even longer. The final approach to equilibrium stretches out across timescales that make trillions of years seem brief. The white dwarf at this stage is barely changing. A few hundredths of a degree per billion years, perhaps. Then a few thousandths of a degree per billion years. The change is real, but it's so slow that it approaches the philosophical boundary between change and stasis. What would this object look like at this stage, if you could somehow perceive it? Imagine an object the size of Earth, floating in absolute darkness, no stars nearby, no reflected light from any source. The object is faintly warm, perhaps 50 degrees above absolute zero. It's radiating in the far infrared, at wavelengths so long that they're closer to microwave radiation than to anything resembling light. No human eye could see it. No optical telescope could detect it. Even the most sensitive infrared instruments currently in existence, instruments like the James Webb Space Telescope, would struggle to detect an object this faint at any significant distance. It would be, for all practical purposes, invisible, a dark, dense sphere drifting silently through an empty universe. But it's still there. That's the remarkable thing. The mass hasn't gone anywhere. The matter hasn't disappeared. Every carbon atom, every oxygen atom, every crystallized ion in its interior is still present. The white dwarf still has the same gravitational pull it had when it was blazing hot. It still warps the fabric of space-time around it. If something were to pass close by, a rogue planet, a stray asteroid, a passing piece of debris, it would feel the white dwarf's gravity. It would be deflected, pulled, potentially captured into orbit. The white dwarf is invisible, but not absent. It's dark, but not gone. It occupies space. It has mass. It interacts gravitationally with its surroundings. It simply stopped communicating through light. It has gone silent in the electromagnetic spectrum, but it hasn't ceased to exist. There's a strange poetry to this transition. For billions of years, the white dwarf has been defined by its light. It was found by astronomers because it glowed. It was studied because it emitted radiation that could be analyzed. Its temperature, its composition, its age, all were deduced from the light it produced. Light was its voice, its way of announcing its presence and telling its story to anyone with a telescope, and the knowledge to interpret what they saw. And now, as it cools below the threshold of detectability, it loses that voice. It becomes a silent object in a silent universe, still present, still massive, still real, but no longer able to speak through light. This raises a fascinating question about observation and existence. If an object exists but cannot be detected by any electromagnetic means, how do we know it's there? In the far future, any civilization that somehow endured into this dark era would face this problem. The universe around them would be filled with the remnants of dead stars, white dwarfs that have cooled beyond detectability, neutron stars that have radiated away their heat, black holes that emit only the faintest trickle of Hawking radiation. These objects would make up a significant fraction of the total mass in the galaxy, but they would be effectively invisible. A future astronomer peering out into the darkness would see almost nothing, unaware that the space around them was populated by the silent corpses of trillions of dead stars. We face a milder version of this problem today. Even now, the coolest white dwarfs are extremely difficult to detect. They're so faint that even powerful telescopes can only spot them if they're relatively nearby, within a few hundred light years. Beyond that distance, they fade into the background noise. Astronomers estimate that there could be billions of white dwarfs in the Milky Way that we haven't detected yet, simply because they've cooled to the point where they're too faint for our current instruments. They're out there, drifting through the galaxy, massive and dense and real, but invisible to us. Dark objects in a bright universe. In the far future, the ratio will flip. The universe itself will be dark, and these objects will make up much of what remains. Let's linger for a moment on the timescales we're discussing, because it's important to feel the weight of them. The universe right now is about 13.8 billion years old. That is already an almost incomprehensible span of time. Human civilization has existed for roughly 10,000 years. Written language for about 5,000. Modern science for a few hundred. The entire history of everything humans have ever done occupies a vanishingly small sliver of cosmic time. And the universe at 13.8 billion years old is considered young by the standards of white dwarf cooling. The youngest white dwarfs, the ones that form most recently from recently deceased stars, have barely started their cooling journey. The oldest white dwarfs, formed from the first generations of stars that died more than 10 billion years ago, have been cooling for most of the universe's history, and they're still at several thousand degrees. They're still glowing. For a white dwarf to cool from its initial temperature to below the threshold of visible light requires roughly 15 to 20 billion years, depending on its mass and composition. That's longer than the current age of the universe. For it to cool into the deep infrared, below 1,000 degrees, requires perhaps 50 to 100 billion years. For it to cool to the temperature of a warm room, around 300 Kelvin, might take hundreds of billions of years. For it to cool to within a few degrees of absolute zero, approaching thermal equilibrium with the cosmic microwave background, requires trillions of years. And for it to reach the point where it has effectively stopped cooling entirely, where the temperature difference between it and the surrounding universe is negligibly small, that requires timescales so vast that even trillions of years understate them. At each of these stages, the white dwarf's appearance changes, or rather, its appearance fades. At 15 billion years, it's a dim red point of light, barely visible. At 50 billion years, it's invisible to the eye, but detectable in the infrared. At 500 billion years, it's detectable only with the most sensitive instruments imaginable, instruments that might not even be buildable with known physics. At 5 trillion years, it's a dark, cold object, indistinguishable from the empty space around it by almost any measure. The transition from brilliant star remnant to invisible dark mass is complete. Not through any sudden event, but through the patient grinding arithmetic of thermodynamics. A hot object radiates. As it radiates, it cools. As it cools, it radiates less. As it radiates less, it cools more slowly. And this cycle repeats, over and over and over, each iteration taking longer than the last, until the amount of radiation being emitted is so small that it becomes essentially nothing. The universe in which this final fading occurs will be profoundly different from the one we inhabit. The accelerating expansion of space, driven by dark energy, will have pushed most galaxies far beyond the observable horizon. The local group of galaxies, the Milky Way, Andromeda, and their smaller companions, will have long since merged into a single large elliptical galaxy. But beyond that merged structure, nothing will be visible. Every other galaxy will have receded beyond the point where its light can reach us. A future observer in that merged galaxy would look out and see only darkness, unaware that trillions of other galaxies ever existed. The universe of the far future is a lonely place, and the white dwarfs cooling within it are lonely objects, surrounded by the remnants of dead stars, drifting through a galaxy that no longer produces light, orbiting a galactic center dominated by a massive black hole that itself is slowly evaporating through Hawking radiation across timescales that dwarf even the white dwarf's cooling time. But the white dwarf endures. It doesn't evaporate like a black hole. It doesn't decay, as far as we know, on these timescales. The protons and neutrons that make up its carbon and oxygen atoms are stable, or at least so incredibly long-lived that their decay time vastly exceeds the cooling time. The crystallized core remains intact. The mass remains. The gravitational presence remains. The white dwarf persists as a physical object long after it has ceased to be a luminous one. It becomes a relic, a fossil, an artifact of a brighter age, preserved not in amber or stone, but in the crystalline lattice of carbon and oxygen atoms that were forged in the heart of a star that died billions or trillions of years ago. And this is what gives the fading of a white dwarf its peculiar emotional resonance. It's not a violent death. It's not dramatic. It's the opposite of dramatic. It's the longest, slowest, quietest decline imaginable. A star that once shone, that once lit up the space around it, that once warmed planets and drove weather patterns and made photosynthesis possible, reduced over trillions of years to a dark, cold, silent mass that no instrument could detect and no eye could see. The light didn't go out in a flash. It went out one photon at a time, each photon a little less energetic than the one before, each one carrying away a little less heat, each one marking one more infinitesimal step on the long, long road from brilliance to darkness. There is no moment you can point to and say, that is when it stopped shining. Because it never truly stops. It just gets dimmer and dimmer and dimmer until the distinction between shining and not shining becomes meaningless. The light doesn't end. It dissolves. And somewhere out there, trillions of years from now, in a universe so dark and cold and empty that it bears no resemblance to the cosmos we know, the remnant of a star that once burned for billions of years will finally reach a point where its temperature is barely distinguishable from the void around it, where its radiation is so feeble that it contributes essentially nothing to the energy budget of the universe, where it has become, for all practical purposes, as cold and dark as space itself. This remnant will still exist. It will still have mass. It will still be composed of crystallized carbon and oxygen in a structure supported by electron degeneracy pressure. It will still be Earth-sized and sun-massed, but it will no longer glow, no longer radiate in any meaningful sense, no longer announce its presence through light of any wavelength. It will have become something that has never existed before in the history of the universe. Something the cosmos has not yet had time to produce. A completely cooled stellar remnant. A dark, cold, silent sphere of crystallized matter, drifting through the void for eternity. And that object has a name. Astronomers call it a black dwarf. And the fact that no black dwarf has ever existed, that the present cosmos has not existed for even a fraction of the time required for any white dwarf to complete this journey, is one of the most profound truths in all of astrophysics. What a black dwarf truly is, why none exist yet, and what kind of universe would finally contain one, that is where this story arrives at its deepest and most haunting conclusion. A black dwarf is one of the strangest objects in all of astrophysics. Not because of what it does, but because of what it doesn't do. It doesn't shine, it doesn't radiate any meaningful heat, it doesn't undergo fusion or fission or any energetic process. It simply exists. An Earth-sized mass of cold crystallized carbon and oxygen, carrying roughly the weight of the sun, producing no light, no heat, no signal of any kind. An Earth-sized mass of cold crystallized carbon and oxygen, carrying roughly the weight of a sun, producing no light, no heat, no signal of any kind. It is the final state of a white dwarf, the endpoint of the longest cooling process in nature, the last whisper of a star that burned for billions of years, reduced over trillions more to an object that produces no light, no heat, and no signal of any kind. And here is the fact that makes the black dwarf one of the most extraordinary concepts in all of science. Not a single one has ever existed. Anywhere. In the entire observable universe. The universe is simply not old enough. Let that sink in for a moment. The universe is 13.8 billion years old. It has existed for a span of time that dwarfs every human timescale imaginable. It's roughly 3 times older than Earth itself. It's 1 million times older than the entire history of our species. It contains everything that has ever happened, every star that has ever formed, every galaxy that has ever assembled, every atom that has ever been fused inside a stellar core. And in all that time, across all that history, not one white dwarf has had time to cool completely. Not one has reached the black dwarf stage. Every white dwarf that has ever formed, from the earliest ones created by the first generation of massive stars over 12 billion years ago, to the ones being born right now from dying sun-like stars across the Milky Way, every single one of them is still warm, still radiating, still somewhere on the long downward slope of its cooling curve. The oldest white dwarfs have been cooling for roughly 10 to 12 billion years, and they're still at several thousand degrees at their surfaces. They have barely begun. To understand why the black dwarf remains purely hypothetical, you need to grasp the timescale required. And this is where numbers start to lose their ability to convey meaning. The estimated time for a typical white dwarf to cool to a temperature effectively indistinguishable from the cosmic background, to reach the state we'd call a black dwarf, is on the order of 10 to the 15th power years. That is a 1 followed by 15 zeros. 1 quadrillion years. To put this in perspective, the current age of the universe is about 13.8 billion years. A quadrillion years is roughly 100,000 times the current age of the universe. If you represented the entire history of the cosmos, everything from the Big Bang to this exact moment, as a single grain of sand, then the time required for a white dwarf to become a black dwarf would be a pile of sand containing 100,000 grains. We are 1 grain into a pile of 100,000. Try yet another angle. Imagine you laid out the entire history of the universe, all 13.8 billion years of it, as a single page in a book. A book containing the full cooling story of a white dwarf would be 100,000 pages long. We've read one page out of a volume so thick you couldn't lift it. couldn't fit it on any shelf, couldn't read it in 1,000 human lifetimes. Everything that has ever happened, the Big Bang, the formation of the first galaxies, the birth and death of countless stars, the origin of life on Earth, the rise of human civilization, all of it fits on that single opening page. The remaining 99,999 pages are blank to us, unwritten, unwitnessed. They belong to the white dwarf alone, sitting in the dark, cooling degree by fractional degree, filling those empty pages with the quietest, slowest story ever told. The universe has completed roughly 100,000th of the journey necessary to produce a single black dwarf. Or try another comparison. If the entire current age of the universe, all 13.8 billion years of it, were compressed into a single second, then the cooling time of a white dwarf would be roughly 1.25 days. We've experienced 1 second of a process that takes more than a day. We've barely started. The movie has just begun to play and we're still watching the opening frame. The reason for this extraordinary duration comes back to the same physics that governs all radiation. The cooling rate of a white dwarf is governed by the Stefan Boltzmann law, which says the radiation rate depends on the 4th power of the surface temperature. As the white dwarf cools, the radiation rate plummets. Each successive degree of cooling takes longer than the last. The final stages of cooling, when the white dwarf is only a few degrees above the temperature of the surrounding universe, take an almost unimaginably long time. The temperature difference between the white dwarf and the cosmic background becomes so small that the energy being radiated is vanishingly tiny. The white dwarf approaches equilibrium asymptotically, creeping toward the temperature of the void degree by degree, fraction of a degree by fraction of a degree, with each increment taking billions or trillions of years longer than the one before. And the target itself is moving. The cosmic microwave background, the ambient temperature of the universe, is currently about 2.7 Kelvin, just a few degrees above absolute zero. But the universe is expanding, and as it expands, this background radiation stretches and cools. Trillions of years from now, the cosmic background temperature will be a tiny fraction of a Kelvin, far colder than it is today. So the white dwarf isn't just cooling towards a fixed target, it's cooling towards a target that is itself sinking ever closer to absolute zero. Both the white dwarf and the universe are cooling, but the universe cools faster because the expansion of space stretches the background radiation relentlessly. The white dwarf is chasing a receding finish line. It will eventually catch up, in the sense that the temperature difference between it and the background will become negligibly small. But this convergence takes even longer because both temperatures are dropping. Now, what kind of universe would contain black dwarfs? What does the cosmos look like at the timescales where white dwarfs have finally finished cooling? The answer is almost incomprehensibly bleak, at least from the perspective of any living being adapted to the bright, active universe we inhabit today. By the time the first black dwarfs begin to appear, roughly a quadrillion years from now, the Stelliferous era will be a distant memory. Star formation will have ceased entirely, perhaps hundreds of billions of years earlier. The last red dwarfs, those tiny patient stars that can burn their hydrogen for trillions of years, will have exhausted their fuel and died, each one leaving behind its own small white dwarf remnant that then begins its own long cooling journey. The Milky Way and Andromeda will have merged long ago into a single large elliptical galaxy, sometimes nicknamed Milk-O-Me-Dar. But this merged galaxy will be dark. No stars will shine within it. No nebulae will glow, No new solar systems will form. The galaxy will be a vast collection of stellar remnants, white dwarfs in various stages of cooling, neutron stars that have long since radiated away their heat, black holes of various sizes, gradually losing mass to quantum effects over timescales that dwarf even the white dwarf's patience, and whatever planets and debris remain in orbit around these dead objects. Gravitationally, the galaxy will still function. Stars may be dead, but their remnants still have mass. White dwarfs, neutron stars, and black holes will still orbit the galactic center. Planets, if they survive the death of their parent stars, will still orbit their remnants. Moons will still orbit planets. The gravitational architecture of the galaxy remains intact, but it will be architecture without illumination. Imagine a vast city where every building still stands, every road still connects, every structure is perfectly intact, but every light has been turned off. The city is there. You could navigate it if you had some way to see, but there is nothing to see by. The galaxy in the degenerate era is a structure defined entirely by gravity and populated entirely by objects that produce no light. A skeleton of a galaxy, with all the mass but none of the radiance. And beyond this dark galaxy, nothing. The expansion of space will have long since carried every other galaxy beyond the reach of light. The universe outside will be a perfect, featureless void, but within the galaxy itself, activity of a kind persists. Rogue planets, flung from their orbits during stellar death, will drift between remnants. Occasionally, two dark objects will pass close enough to perturb each other's trajectories. Once in a great while, measured across timescales of trillions of years, two remnants might collide, producing a brief flash of energy in an otherwise lightless cosmos. These events will be vanishingly rare, but they will happen. The galaxy is not frozen. It is merely dark. Gravity still operates, objects still move, the machinery of physics still turns, but there's no light to see it by, no warmth to sustain anything that might want to watch. In this dark, cold, lonely cosmos, the white dwarves would be among the warmest objects in existence. Even at just a few degrees or a few tens of degrees above absolute zero, they would be warmer than the cosmic background. They would be faint embers in an ocean of darkness, radiating their last reserves of heat into a universe that has essentially reached its minimum energy state. And one by one, across spans of time that stretch into the quadrillions of years, they would finally reach equilibrium. Their surface temperatures would drop to match the background. Their radiation would dwindle to nothing, and they would become black dwarfs, dark, cold, silent, and invisible. The last transformation of a stellar life that began with the ignition of nuclear fusion in a cloud of collapsing gas, perhaps 20 or 30 or 50 trillion years earlier. The black dwarf, once formed, would be an extraordinarily stable object. It's supported against gravitational collapse by electron degeneracy pressure, which doesn't depend on temperature. Even at absolute zero, the quantum mechanical pressure of its electrons would hold it up. It wouldn't collapse further. It wouldn't explode. It wouldn't do anything. It would simply persist. A sphere of crystallized carbon and oxygen with the mass of a star and the size of a planet, floating through the void essentially forever. Or would it? This is where the story takes one final, speculative turn into the deepest reaches of theoretical physics. Because the question of whether a black dwarf truly persists forever depends on something we don't yet know for certain. It depends on whether protons decay. In the standard model of particle physics, protons are stable. They don't decay. A proton left alone will exist forever. This means the atoms that make up a black dwarf, the carbon and oxygen nuclei in its crystallized core, would also last forever. The black dwarf would be eternal, drifting through the void for all of time, unchanged and unchanging. But some extensions of the standard model, particularly grand unified theories that attempt to unite the fundamental forces of nature, predict that protons are not truly stable. They predict that protons have an incredibly long but finite lifetime. The predicted half-life of the proton in these theories varies, but typical estimates range from about 10 to the 34th power years to 10 to the 41st power years. These numbers are so large that they make the cooling time of a white dwarf look almost reasonable by comparison. 10 to the 37th power years, a commonly cited middle estimate, is a 1 followed by 37 zeros. That's roughly 10,000 trillion times the current age of the universe. Even in the context of the deep future, where we've already been discussing quadrillions of years, proton decay operates on timescales that are vastly inconceivably longer. But if protons do decay, then even the black dwarf is not permanent. Over these almost inconceivable spans of time, the protons and neutrons that make up the carbon and oxygen atoms in the black dwarf's core would gradually decay. The decay products would be lighter particles, positrons and pions that would quickly convert into photons and neutrinos. The black dwarf would slowly, imperceptibly erode, atom by atom, nucleus by nucleus. Its mass would decrease with agonizing slowness. The process would take so long that if you checked on the black dwarf every trillion years, you wouldn't notice any change. But over 10 to the 37th years, or 10 to the 41st years, the decay would be complete. The black dwarf would have dissolved into a faint mist of radiation and subatomic particles, dispersing into the void. The last trace of the original star, gone. Physicists Fred Adams and Gregory Laughlin, in their landmark study of the long-term future of the universe, laid out these timescales with remarkable clarity. They described successive eras of cosmic history, each one vastly longer than the last. The stelliferous era, the age of stars, lasts perhaps 100 trillion years. The degenerate era, dominated by stellar remnants like white dwarfs and black dwarfs, could last from 10 to the 15th power years to 10 to the 37th power years, depending on whether proton decay occurs. If protons are truly stable, then the degenerate era lasts essentially forever. The black dwarfs persist for all eternity. If protons decay, then the degenerate era eventually ends when all the remnants have dissolved. Either way, the timescales are so extreme that every event in the history of the universe up to now, the Big Bang, the formation of the first stars, the assembly of galaxies, the origin and evolution of life on Earth, all of it occupies an infinitesimally thin sliver at the very beginning of cosmic history. Everything we know, everything we've ever experienced, everything that has ever happened is the opening sentence of a story that will run for chapters longer than we can count. There is one more speculative possibility worth mentioning. Even if protons are stable and the black dwarf persists forever as a solid crystallized mass, there is a process that could, on truly unimaginable timescales, transform it further. Quantum tunneling. In quantum mechanics, particles have a small but non-zero probability of tunneling through energy barriers that they couldn't classically overcome. This means that over sufficiently long timescales, the atoms in a black dwarf could slowly rearrange themselves into lower energy configurations. Carbon and oxygen atoms could, through quantum tunneling, undergo nuclear reactions that wouldn't be possible at the black dwarf's frigid temperature through any classical process. These tunneling reactions would convert the carbon and oxygen into iron 56 and nickel 62, the most stable nuclei in nature, the lowest energy state for nuclear matter. The timescale for this process is estimated at roughly 10 to the 1500th power years. That is a 1 followed by 1500 zeros, a number so extreme that writing it out would fill an entire page with nothing but zeros. This is so far beyond any other timescale we've discussed that it almost defies mention. But in the context of eternity, if eternity is truly what awaits the black dwarf, then even this process eventually completes. The black dwarf, over timescales that reduce everything else in cosmic history to absolute insignificance, would slowly transmute into a sphere of iron, the most stable element, the lowest energy state of nuclear matter, the absolute rock bottom of nuclear physics. Whether this actually happens, whether protons decay first, whether some other process intervenes, is unknown. We're deep in the realm of speculation here, extrapolating the laws of physics across timescales so extreme that we can't be certain those laws even apply. Physics as we understand it might be incomplete. There might be processes we haven't discovered that become important on these timescales. The universe might surprise us, as it has so many times before. But based on what we currently know, these are the possibilities. The black dwarf either persists forever as a cold crystal, or slowly dissolves through proton decay, or slowly transmutes into iron through quantum tunneling. All three outcomes are extraordinary. All three occur on timescales that make the current age of the universe seem like a heartbeat. Let's step back now, away from the speculative far future, and return to the present moment. Because the most profound thing about the black dwarf isn't the physics. It's what it tells us about where we are right now in the story of the universe. We tend to think of the universe as old. 13.8 billion years is an enormous span of time by any human standard. It's roughly 1 million times longer than the entire history of human civilization. It encompasses the formation of the first stars and galaxies, the assembly of the Milky Way, the birth and death of countless stellar generations, the formation of Earth, the origin of life, the evolution of complex organisms, and the emergence of human consciousness. All of that has happened within the universe's 13.8 billion year history. It feels like a lot. It feels like the universe has been around for a long time. But from the perspective of white dwarf cooling, the universe is young. Astonishingly, almost comically young. The oldest white dwarfs have been cooling for barely 10 billion years. They need a quadrillion years to finish. That's like a baby that has been alive for 5 minutes out of a lifespan of 1,000 years. The universe hasn't yet produced a single black dwarf. It hasn't even come close. The longest cooling white dwarfs in existence are still at several thousand degrees. They're still visibly glowing under the right instruments. They haven't even completed the first major phase of their cooling journey. Everything that has ever happened in the history of the cosmos, every star that has ever shone, every galaxy that has ever formed, every planet that has ever coalesced, every living thing that has ever existed. All of it has occurred within the briefest opening flicker of a process that will continue for timescales. So vast they strain the limits of mathematics to express, let alone human intuition to grasp. This realization rearranges how you see everything. We are not living in the twilight of the cosmos. We are not even living in the midday. We are living in the first fraction of the first second after dawn. The universe is barely awake. The brightest, most energetic, most active period of a cosmic history, the stelliferous era during which stars shine and galaxies blaze and life is possible, is itself just a brief, brilliant prelude to an almost infinitely long aftermath of darkness and silence. The stars, all the stars, every star that will ever exist, are the opening act. The main performance, in terms of sheer duration, belongs to the remnants, the white dwarfs cooling in the dark, the black dwarfs drifting through the void, the slow, patient, quiet aftermath that will outlast the age of stars by a factor of millions or billions or more. And yet, here we are, right now, in the brief, blazing era when stars still shine, when the universe is still bright and warm and active, when new stars are still being born from collapsing gas clouds, when planets are still forming, when life is still possible. We exist in a cosmically privileged moment, not because we're special, but because the conditions that allow beings like us to exist, stars to provide energy, heavy elements to form planets, stable environments to nurture the development of complexity, these conditions exist only during the stelliferous era. Once the last stars die, the universe will still exist, but it won't support life as we understand it. No energy sources to drive metabolism, no temperature gradients to power chemistry, no light to warm worlds. The deep future of the cosmos is a place of extraordinary patience, but no apparent vitality. We live in the one window when the universe is alive in the sense that matters to us. The white dwarf embodies this contrast perfectly. It begins its existence in the age of stars, born from the death of a star that shone for billions of years. It carries within it the heat of that stellar life, the stored energy of billions of years of nuclear fusion. And then it spends an almost incomprehensibly longer span of time slowly releasing that energy, photon by photon, degree by degree, fading from brilliance to invisibility across trillions of years. It is a bridge between two eras, between the bright present and the dark future, between the age when the universe produces light and the age when the universe merely remembers it. Every white dwarf you could point a telescope at tonight is an object in transition. It has already crossed the boundary from living star to dead remnant, but it hasn't yet completed the journey to its final state. It's in between, still warm, still glowing, still carrying the thermal memory of a star that no longer exists, still slowly surrendering that memory to the void. Those billions of white dwarfs scattered across the Milky Way, every single one of them are former stellar cores. Each one is on the same cooling journey. Each one will eventually, given enough time, become a black dwarf. Together, they represent the accumulated remains of most of the stars that have ever lived and died in our galaxy. They are the fossils of the Milky Way's stellar history, each one carrying information about the star it came from, the era in which that star lived, and the processes that shaped it. And every single one of them is still cooling, still changing, still somewhere on the long road between the heat of stellar life and the cold of eternal darkness. When you look up at the night sky on a clear evening, you see stars, thousands of them, scattered across the darkness, each one a sun, each one burning through its own supply of nuclear fuel. And somewhere among them, though you cannot see them with your naked eye, are the white dwarfs, faint, tiny, incredibly dense points of light. Remnants of stars that died millions or billions of years ago. Stars that once shone as brightly as the ones you see now. Stars that once had planets, perhaps even life. Stars that are now gone, leaving behind only these small, dense embers slowly cooling in the dark. Those embers will outlast everything you see in the sky tonight. They will outlast every star currently burning. They will outlast the Milky Way as a star-forming galaxy. They will outlast the era of starlight itself. Long after the last living star has exhausted its fuel and gone dark, the white dwarfs will still be there. A little cooler, a little dimmer, but still present. Still patiently surrendering the last inherited warmth of a star that burned out eons ago. And they will continue cooling for trillions of years beyond that, fading into the darkness of a universe that has itself gone dark, approaching a final state that no observer will ever witness, because there will be no observers left to witness it. The black dwarf is the universe's longest goodbye, a farewell that takes longer than anything else in nature, longer than the life of any star, longer than the age of any galaxy, longer than the current age of the cosmos itself, by a factor so large that the comparison breaks down. It is the last stage in the life of a sun-like star, and it has never happened. Not once, not anywhere. The universe is too young. We are too early. The story of the white dwarf's cooling is still in its opening pages, and the final chapter won't be written for timescales that reduce everything we know, everything we are, everything we have ever experienced, to a single imperceptible flicker at the very beginning of an almost endless dark. And there is something quietly magnificent about that. Not because the darkness is beautiful, but because we're here before it arrives. We exist in the bright opening chapter. We are made of atoms forged in the cores of stars that lived and died before our sun was born. We walk on a planet warmed by a star that will itself one day become a white dwarf. And we have the capacity, the consciousness, the sheer improbable awareness to look out at the universe and understand what is coming. To see the white dwarfs cooling in the dark and know what they are. To comprehend the timescales involved and feel their weight. To understand that we live in the one brief moment when the universe is lit up. And to appreciate that light for what it is. A temporary, precious, extraordinary thing. A flash of warmth and brilliance in a cosmos that will spend most of its existence in cold and silence. The stars are still shining tonight. The white dwarfs are still cooling. The black dwarfs have not yet arrived. And you are here, in the brief, bright window, able to wonder about all of it. That, by any measure, is remarkable. Sleep well under the stars. They won't burn forever. But right now, tonight, they are still here. And so are you.